Hi, Mr. Crone here again with my series of conceptual physics, and today we're going to take on the concept of acceleration. So this will sort of introduce us to this new idea of acceleration, and obviously we'll start with the definition, but we'll kind of break it down into what exactly this definition means. You know, oftentimes the definitions are very technical, they're maybe a little hard to understand, but the idea behind acceleration is not difficult to understand. So let's start with the definition and then we'll go to a simplification. So the definition of acceleration is how much your velocity is changing by per second, but I want to use a specific mathematical term because we use the same thing when we were talking about velocity, and that is a ratio or a rate. So the acceleration is the rate of change of velocity per time. So in other words, per second, how much does the velocity change by? So you can imagine if you had a very high acceleration, like maybe 500, say, well, in each second, the velocity is changing by 500. That's quite a big acceleration. Whereas if the acceleration was only maybe 2, then you would say, well, every second, my velocity only changed by 2, so that's not really that much of a change. That's something that any person would be able to handle. So acceleration is the next level of motion from what we were talking about with velocity. Velocity was the rate of change of displacement. And now we're going forward to see, well, velocity can of course change, and acceleration is a way to put a number. We want to put a cold, hard number on how much did the velocity of this thing change, and the acceleration is the way in which we do that. So a large acceleration means your velocity is changing very quickly, and when your acceleration is very small, then it means your velocity is still changing, but it's just not doing so nearly as quickly. So let's give a little simpler definitions. Let's not be quite so technical with this. What does it exactly mean? It is how quickly the velocity is changing. How quickly the velocity is changing. Now, obviously there's an equation for acceleration because it is something that we want to be able to calculate, and because it is a rate, that means it is a numerical value, and all I need to do is to divide, because a rate is a comparison that is done by dividing. We're going to divide the change in the velocity by the amount of time, and we'll get the acceleration. And it's going to have new units because we've never seen this combination of properties before. So the equation is that A, and I'm going to put that little vector symbol over it to indicate that it does have direction. It matters which direction the acceleration is pointed, and we're going to talk about that in just a moment. But essentially, it's the change in the velocity, so it's v minus v naught divided by t. It's the change in the velocity, which is the final minus the initial, and then we just divide it by the time, and that is going to give us a number that's going to allow us to compare objects in terms of how quickly they change their speed. Now, obviously, this is a new equation, so we've never seen this one before. So we want to think about what the units for this are. This is going to be meters per second on the top, and on the bottom, it would just be seconds. It may not be obvious to you, but I'm going to show you real quickly. The way that you would do this is when you divide by a number like this, you have a fraction divided by something, we're going to turn this into s divided by 1. So the way you divide by a fraction is you multiply by the reciprocal. So I'm going to leave the top alone, meters per second, but I'm going to multiply instead of dividing. Instead of multiplying by s, I'll multiply by 1 over s. That's the reciprocal of s. And 1 over s gives me meters per second squared. So that's an unusual unit. That's an unusual unit, but I will say this. That is something we have never seen before. We've seen meters per second, but we've never seen meters per second squared, so that's something that should make this new property really stand out. That should make it easy for you to identify. If I give you an acceleration, I will almost always say that it's the acceleration, because I feel like at this level of the motion, to just say that somebody was traveling with 5 meters per second squared, that just feels a little bit too vague. So I might say they were traveling with 5 meters per second. I think that's fair to say that they have some velocity. But to give the acceleration without saying the word acceleration, it would just be really unusual. That's just really, really unusual. So when you're looking at a problem, it should probably say the acceleration is, or an acceleration of, or it's accelerating at. And those are all things that would indicate that that is the acceleration. But even if I don't say that, if you see units of meters per second squared, that is an acceleration. There is no other property that would have those same units. So as you can see, the units are quite complicated because we're moving up the levels of motion. So let's just make it a little bit more clear what I mean when I say the levels of motion. I'm going to review backwards to when we first started on this at the beginning of the school year and just go through some of the details that we've learned so far. I'm just kind of summarizing all the stuff that we've learned so far. And I'm going to be using some of the symbols, so you want to make sure that you really pay attention to those symbols that we use. When we think about the position of an object, just where is the object at? We normally use the number line, or like the x-axis on a graph. That's the easiest way. We use this imaginary number line, we kind of lay it on reality, and we say, well, we'll measure compared to this number line. So things move from one place to another, that means they have displacement. If we measure how fast they did it, we could figure out the velocity. And if their velocity changed during that period of time, then we could also figure that one out too. So I'm going to go through the symbols across the top row here. For position, normally we use the letter X. Sometimes we use the letter Y, or we might even use the letter Z, and that's just to account for the 3 dimensions. So we have horizontally going like this, up and down would be the Y-axis, and then going this way away from me or towards me, I would call that the Z-axis. Now in this class, we will never get to the Z-axis. We're not going to look at anything quite that complicated, but we will look at things both horizontally, and I would say that X would be the best letter to represent the position of something horizontally, but if we go vertical, we like to use the letter Y, because the Y is represented by the Y-axis on the graph. So we kind of take advantage of the same things you use in your math class. You know Y is up is positive, down is negative. Let's just use that. That number line already exists, and we can just take advantage of what you already understand about that. Now I'm going to share with you a new symbol for displacement. This is really important because we're moving up to the next level. Everyone hopefully has a really good understanding of velocity at this point. And so now it's time to just open up a little bit more to some of the other ways in which displacement could be expressed to you. It is normally expressed with the symbol D, and that's what everyone should be very familiar with that one. Or it might be, and the way you would say this is delta X. That is the Greek letter delta. So you say delta X. And what delta X means is the change in the position. So listen, if I'm standing at the 5 meter mark and I move to the 8 meter mark, my displacement is 3 because that's how far away I am from my starting point. So you can use the letter D, or you can replace it with delta X. And you'll see that in positive physics, and you'll see that in other places too. In some of the textbooks, the delta X, it means exactly the same thing. How far you have changed your position, that is your displacement. Because by definition, it's how far you are from your starting point. Okay, now velocity was really easy because we just used the letter V, and there's really no other symbols. Please don't use the letter S, which is some people were using for speed, but you don't want to do that. The letter V for velocity, and if you take the little vector symbol off, then it's called speed. And the difference would just simply be that speed would not have direction. Speed would still tell you how fast you're going, but it would not tell you what direction you were going. Whereas velocity should say either positive or negative, or it might say north-south, east-west, or even like left or right. There's lots of ways you can give the direction for something, but velocity should have some direction because without it, it doesn't really have as much meaning. And then for acceleration, as we've already said, the symbol is A. That's pretty straightforward. We use the letter A to represent the acceleration. Equations. Well, there is no equation for position because position is just something that you read off of the, you just either read off the graph or it would be given to you in the problem. But displacement, that guy does have a formula. Remember, I can say D or I can say delta X. That would be equal to the final position minus the initial position. Okay, pretty much exactly what you would think. The same way we did the change in any property. It's always the final version or value of that property minus the initial value of the property. It could be your weight, the amount of money you have, it could be anything, the date, time, any of these things, whatever the final value was, you subtract the initial one. So if I say that I started at the 5 and I ended at the 8, then 8 minus 5 is 3. That's my displacement. That's how far I have been displaced from my original starting position. Okay, now we're going to use this to move over to the next box because V, which you have learned as D over T, and that's totally true. That's still true. But we also, you might see it as delta X over T. It's exactly the same equation. We're just going to start getting used to this new symbol that delta X can also be used to represent the change in the position, which is the same thing as the displacement. And then of course for the acceleration, that is just the change in V over the change in time. The change in the velocity divided by the change in the time. Okay. Now, as we move up through these different levels of motion, you'll see that the units start getting more and more complicated, because when we first started with position, well, position is going to be in meters. You say, like, I'm at the 3 meter mark, I'm at the 8 meter mark, I'm at the 5 meter mark. But when you go to displacement and you subtract those two positions, it still gives you the same unit. In fact, you can only do subtraction if they have the same units. So for example, you could not subtract seconds from meters, because it doesn't become a new thing. It just becomes meters minus seconds. So because this was in meters and this guy would also be in meters, when I subtract them, I will still get meters. But then when I take it to velocity, I'm going to divide by the time. So now I would end up with meters per second. And then finally, I would end up with meters per second squared for this guy right here. Okay, so all that's good. We've established that there is a formula for acceleration, and we're going to practice with that formula. But for right now, what I want to really think about is, what is the meaning of the acceleration, and how do you know what the direction of the thing is? So I'm just going to revisit back here with my units. I just want to remind you that this was meters per second, and that actually is a way that you can say it. You could also say meters per second divided by seconds. And what I like about that, which is a little unusual, but in England, that is actually how they say it. They don't say meters per second squared usually. They would say meters per second. But it actually does kind of make sense, because if you just think about what is the acceleration, it's how much your meters per second are going to change in every 1 second. So meters per second does actually make sense. In fact, any unit with one distance and two time units, that would be considered an acceleration. So for example, when you're in your car, you probably don't measure your speed in meters per second. You use miles per hour. But does your speed change over hours? I would say no, it changes over a few seconds. So could you have miles per hour per second? Yes, definitely. Of course you could. How much do the miles per hour of your velocity change in every 1 second? That's a fair acceleration. Now, we'll use meters per second as our standard. But any unit of distance divided by 2 units of time, that is an acceleration for sure. And this way of thinking of it, meters per second, I think is really important. Because if I tell you that my acceleration is 2 meters per second, what that means is that every second, my velocity will increase by 2 meters per second. So if I started at time equals 0 with 0 velocity, at the end of 1 second, I would be moving at 2 meters per second. At the end of 2 seconds, I would be moving 4 meters per second. At the end of 3, I'll be moving 6, and then 8, and then 10, and so on. Every second, I gain 2 meters per second. So I see my velocity is growing, it's increasing, and increasing its value. Okay, so with regard to the direction, that is a bit of a slippery slope, and it's very easy to get confused. I think that a lot of times people believe that if it's a negative acceleration, that automatically means it's slowing down, but that actually is not true. It's not true. If I am moving in the negative direction, then speeding up would be becoming even more negative. And so even though it might seem like the number is becoming more and more negative, I wouldn't say I was slowing down. I would say I was speeding up, but in the negative direction. You know, it's not considered to be slower if I go to the left than if I go to the right. It doesn't have anything to do with the speed of the thing. It's just simply telling you whether it's traveling one way or the other. So the direction can be really, really tricky. And so just to make sure this is really clear, if the velocity is positive and the acceleration, and, let me do it this way, and A is positive, then that is going to be speeding up. So if I have positive velocity and I add positive acceleration, that means I'm going to be adding to my velocity in each second. Then that means I'm speeding up. I started with some positive value and I'm making it even more and more positive. But if V is negative and A is negative, that is also speeding up. But it would be speeding up in the downward direction. We're going to see that a lot. When we talk about gravity, gravity makes things speed up in the downward direction. So just because the acceleration is negative, that doesn't mean that it's necessarily slowing down. If I threw my pen up in the air, then yes, gravity would definitely slow this thing down and bring it to a stop. But it wouldn't stop there. It would then speed it up back in the downward direction. So what essentially you have to really understand is that when the acceleration points in the same direction as the velocity, then that's going to be speeding up, whether that's in the upward direction or whether that is in the downward direction. So then how do you get slowing down? Well, imagine that you had a velocity that is positive, maybe it's positive 20, and A is negative. Okay, well now that means your positive velocity is going to be getting reduced, because instead of adding to the velocity, now you're subtracting from the velocity. So if I start with a velocity of 10 and I have an acceleration of -2, at the end of the first second, I'll be at 8, then I'll be at 6, then I'll be at 4, then I'll be at 2, then I'll be at 0. Then if it continues, then I will actually start speeding up, but now in the negative direction, because now I will be back to this situation. Once I get down to 0 velocity, if I start moving in the negative direction, now the acceleration and the velocity are pointing in the same direction, and I would be speeding up in the negative direction. So what's important is when the acceleration and the velocity point against each other, that's when you have slowing down. That's what it means to slow down. And obviously there's only one other case that we haven't talked about. That is the V is negative. So you're moving in the downward direction, for example, and A is positive. This would also be slowing down. So if I'm moving in the downward direction, but my acceleration is in the positive direction, what that means is that it's bringing me to a stop. So imagine that if I put a weight on a spring and I let it just start falling, but that spring would start to pull on it and slow it down. That's because the spring is pulling up on the object while it was moving in the downward direction. And whenever the acceleration and the velocity point in the opposite direction, then we end up with slowing down. When they go together, whether they are both up or both down, that is going to result in an object speeding up. And anytime they oppose each other, then that's when we're going to see the objects are slowing down. So that's sort of the basics of acceleration. We'll do some example problems in one of the upcoming videos. But for right now, I think we've laid out all the basics for acceleration. And we'll see you in the next video.